Okay, so this is a question that's asking to find the electric field in a hydrogen atom, and we have to use the quantum mechanics model that tells us that the electrons resulting contribution to charge density is this function here, with rho zero being the normalization factor that we will have to find in a second. A0 is Bohr's radius, and so yeah, so that's what we're going to do. So the first step is we're going to find what that normalization factor rho zero is for that charge density. So if I may write it out, this is number 3. So rho 0r is equal to rho 0 e to the minus 2r over a0. And a0, like we said, is the Bohr's radius. So the first objective here is to figure out what rho 0 is, which is this guy here. Okay. And so for that, what I'm going to do, well, I know that the charge of the electron is going to be negative e. Okay, so if I were to integrate this over a volume, so if I were to get rho 0, if I were to integrate this minus 2r over a0 over the entire space d tau over all v, I'm supposed to get nothing but the charge of the electron, which is minus e. Now, of course, this is a triple integral, so I will get, assuming that rho 0 is a constant, so I will get rho 0 integral e to the minus 2r over a0 d tau. Now this is we're going to do this as is in spherical coordinates, so that's just r squared. So d tau in spherical coordinates is r squared sine theta d theta dr d theta d phi. And of course, phi will take you from 0 to 2 pi. R will, I probably should switch these better theta r. So theta will take you from 0 to pi, complete sphere. And r will definitely go from 0 over all space to infinity. And this is supposed to equal minus e. Now, of course, this is an improper integral. I'm going to assume that some people here at this level of physics have some fairly good understanding of basic calculus, single variable calculus and multivariable calculus. So I'm going to do this in a quick way, just so I don't keep you guys long, because I'm sure you're not here to watch me doing integrals. I'm going to assume some proficiency in that. So this guy here, sine theta d theta, will get us a factor of 2. d phi will get us a factor of 2 pi. From 0 to 2 pi will just be 2 pi. And what I have left, and I have rho 0 outside, and I have left r squared e to the minus 2r over a0 dr, going from 0 to, let's do dummy variables of integration here, since we're going to go from 0 to r, and then when we're done, we're going to take the limit as r goes to infinity. This should be an r prime as well. So r prime is just dummy variable of integration. Now, and this has to equal minus e. Already? Now, of course, I'm sure you recognize this. This is not a very short one. It's integration by parts. It's a polynomial multiplied by an exponential with respect to r. So this is integration by parts done a couple of times. I will assume, again, you guys know how to do that. Just do it a couple of times. The first time takes you down to r. The second time takes you down to an exponential, and then you can integrate that directly. Let me do this on the calculator here. So So if we do this on the calculator, so we're gonna get mine 4 pi rho 0, and we get here a cube over 3 if r is 0. So we're gonna get so I'm doing this on the calculator. So we got a 0 cube over 4 minus a over 4, a 0 over 4, 2r prime squared plus 2a 0 r prime plus a 0 squared e to the minus 2r prime over a 0. Alrighty. And now we're gonna evaluate this guy here from 0 to r, and when we're done, we'll take the limit as r goes to infinity. I could have done this whole thing here on the calculator, but it's fine. So if r is r, we get the same thing. So we get 4 pi rho 0. So it's going to be the same exact thing. So we're going to get, so I'm going to open a gate here, and we're going to get a 0 cube over 4 minus a 0 over 4 2r squared plus 2a 0r plus a 0 squared e to the minus 2r over a 0. This is the first term, the upper bound, minus. Now if I plug in 0 for r, I'm going to get a 0 cube over 4 minus a 0 over 4. First two terms are 0. I get a 0 squared, so this is a 0 cube here, times e to the 0, which is 1. So basically this term goes away to 0. The whole thing is 0. Yeah. Now equals minus e. Okay, and we're gonna take the limit. So let me close this here. And so we're gonna take the limit of this guy as r goes to infinity. So, okay, so we have a polynomial with positive exponents multiplied by an exponential with negative exponents. You're going to get infinity over infinity, of course. And so this is an indeterminate form of L'Hopital's. You're probably going to have to do L'Hopital's here a couple of times. Let's see how many times this is going to cost us. Row 0. First term does not have a L'Hopital's, so I could just leave it here. Minus a 0 over 4. And I have 2r squared plus 2a0r plus a0 squared all over e to the 2r over a0. And then we're going to take the limit as r goes to infinity. uh, equal minus e. Okay, so of course with this guy here, we're gonna get infinity over infinity as we said. So we're gonna do L'Hopital's, whatever you guys want to call it. So L'Hopital's to evaluate the limit. So the next step will be 4 pi rho 0 a0 cube over 4 minus a0 over 4. And with L'Hopital's, we differentiate the top, we differentiate the bottom, and then we re-evaluate the limit. So this is 4r plus 2a0 with respect to r, the derivative with respect to r, and the exponential stays the same, times 2 over a0 by the chain rule. And again, I take the limit. Sorry about that. This pad keeps on disappearing here. Oh, I have the username here ready, so we don't have to take a long time on this. Recent. Oh no, come on. Why are you making me pull this? Okay, so back to this here. Let me just maximize this full screen. So we were taking L'Hopital's on this, and we got, I hope this syncs some of what I wrote so I don't have to repeat it. Doesn't sound like it, so it's fine. 4r plus 2a0 over e to the 2r. No, don't do this. Oh, this is getting really a pain here. Okay, so let's see. 4r plus 2a0 over e to the 2r over a0 times 2 over a0. And then we're going to take the limit as r goes to infinity. I'm going to set this equal minus e. Now again, on this guy here, we're going to get infinity over infinity, right? So one more time, L'Hopital's. So now we will get 4 pi rho 0 a0 q. I mean, the answer will be 0, but I just want to show you the process. So minus a0, because at the end of the day, the exponential will be much larger than a polynomial, and the fraction as r increases will, since the exponential dominates and the exponential is in the denominator, it will drag the whole thing to 0. So we get 4 on top over 2 over a0, 2 over a0 E to the 2R over A0, and there's another 2 over A0 from the chain rule, so we get 2 over A0 squared, and we're going to take the limit, and this is equal minus E here, and we're going to take the limit as R goes to infinity, so we get 4 over infinity, and this whole term goes to 0 as expected, and what we have left is 4 pi rho 0 A0 cube over 4, cross out this 4 with this 4, equals minus E. And so now I could solve for rho 0 finally. So rho 0 will equal to minus E, which is the charge of the electron. This is not E the exponential, this is the charge of the electron, divided by pi A0 cube. So this is after normalizing the charge density function. Okay, so now having done that, now I know that the function will be this function here at the very beginning will just be, so rho of R is equal to minus E over pi A0 cube E to the minus 2R over A0. Okay, and so now we have to find the field. So now that we could go after the field. So let's say that this is the hydrogen atom here. Okay, and what I'm going to do, I'm going to use Gauss's law to figure out the field inside. Gauss's law. Gauss's law says the closed integral of EdA is equal to Q enclosed in a Gaussian surface over epsilon. And let me take my Gaussian surface to be here. Okay, so this is radius R. Okay, and so now, so E is radially outwards, and Gauss's law. Gauss's law will just give me the E. I could, so this will be EdA, but so E is radially outwards. So is the area vector because it's perpendicular to the surface, so they overlap. So the angle between these two is 0. So EdA will become EA cosine 0, which is EA cosine 0 is 1. Cosine 0 is 1, so we will get EA, EdA. And since E is uniform, it's always radially outwards due to the symmetry of the sphere. I could pull that out, and if I pull it out, then this becomes E, and the area of the sphere is just actually, let me do one thing. Let me, before I get the area of the sphere, let me get Q enclosed. So I need the amount of charge that's trapped inside that Gaussian surface there, that red surface. And so I would have, of course, to integrate that because the charge density distribution is not a linear charge distribution. It's not uniform. So therefore, Q enclosed will just equal to rho R d tau. And I would have to integrate from 0 to R, where the radius of my Gaussian surface is. Let's call this R prime, our dummy variable of integration. And so what we will get is, again, I will not repeat the d tau integral. We know that the d tau is sine theta d theta, that will give us 2. D phi will give us 2 pi. This is a spherical volume. And we're going to have left E minus E over pi A0 cubed. This is all constant. I can put it outside the integral. So what I will have left from 0 to R is E to the minus 2R prime over A0 times R prime squared dr. And in fact, I just did this integral not so long ago, except I did it to infinity, and this time I'm doing it from 0 to R, and I did get the answer to be here. Let me do this. So it's the same exact answer we've got before, except we're not going to evaluate the limit. So Q enclosed is equal to minus 4 pi. Pi goes away, cancels out, simplify as we go. So 4e over pi A0 cube. And the integral turned out to be A0 cube over 4 plus or minus actually I'm just going to go to the final answer because it's the same exact integral. And so let me grab that before I took the limit. So that's this guy here. So A0 cube over 4. Yeah, A0 cube over 4 minus A0 over 4 A0 over 4 times let's see here, maybe if I take a picture it'll be faster. Okay, so I've got A0 over 4 2R squared plus 2A0R plus A0 squared e to the minus 2R over A0. That was the answer for that integral. Okay, now let's find the field. So that now that we have the Q enclosed. Yeah, let me see if I could do some simplification here. Actually, I could cross out an A0 with A0 here, and I would get Q enclosed to equal minus 4e over pi. We said pi canceled out, over A0 squared into 1/4 minus 1/4 into 2R squared plus 2A0R plus A0 squared e to the minus 2R over A0. Okay, so back to Gauss's law. E dA equals this whole thing, Q enclosed over epsilon naught. So the area of this the spherical surface is just 4 dA. Since it's uniform, it can just become A, and the area of the sphere is 4 pi r squared times E equals Q enclosed. Let me move this whole thing here because I'm going to use this line here. So over epsilon, and now I'm going to divide by 4 pi r squared. So my E will become, start here, 1 over 4 pi epsilon r squared, and let me copy Q enclosed here. So I will get minus 4e over, oh, I could probably cancel, wait, this 4 with this 4 with this 4. So yeah, so I just have 1 minus this. 1 minus this, yeah. So so we can get rid of this 4 here. And then we have Q over R squared, and we have let's see, E Q enclosed times 1. Let me keep this in red. So 1 minus E to the minus 2R over A0 times 2R squared plus 2A0R plus A0 squared. And of course, this is in the radial direction. So this would be, let me box this nicely. So this would be the electric field. Inside. Okay, let's take a look at the second part. So the second part of the question says, okay, so briefly discuss the advantage of using Gauss's law to find the electric field instead of using Coulomb's law. Of course, the integral is much more simpler. Symmetry plays a big role. It allowed me to pull E outside the integral and to call the integral of dAA, and that ability to pull E from inside the integral to the outside can only work if there's some kind of symmetry in the question. In this case, we have spherical symmetry, and yeah, that does it. Please don't forget to rate, comment, and subscribe.